My name is Naman. I am from Acceleration Robotics. It's really great to see a huge crowd of robotics developers here. Really excited to show our work. So I guess it has been a long day, like listening to all the presentations. So right now I'm going to talk about something that I guess all of us might have faced, issues that you might have faced some while during your robotics development. So how many of you here work on simulations? I guess most of us have. What's your preferred like software for simulations? I guess most of us work with Gazebo. Everyone loves Gazebo, I guess. Right now there is a newer version of Gazebo called Ignition Gazebo, which provides a lot more modularity and basically what you can say a lot more features that more than what classic Gazebo used to offer, right? So today I am going to focus most about outdoor navigation, like outdoor simulations only. So let's say you have a self-driving car. So, like you can't actually test self-driving cars in the real world. Obviously, like I'm not here to sacrifice my life on an untested robot. So that's why we need simulations firsthand, because to test those things in a simulated environment rather than testing it in real life, it can be dangerous to human lives as well and to the $1 million car. So let's start with this. So my most focus would be on how to bridge the reality between simulations to actual real robot, because it actually doesn't make sense if your algorithms work in simulations and not in the real robot. So I'm here to like show you our work. So this work was done in collaboration with the CARE, Center for Artificial Intelligence Robotics here in Bangalore. So yeah, let's begin. Oh yeah, yeah. So first the context of the problem. So obviously we have Ignition Gazebo, now GZ Sim. So why do we need such a simulator? Why do we need some custom things to actually work on it? So everyone knows this robot, right? Yeah. Turtlebot. So what does a basic Turtlebot simulated environment looks like? So there are no rough terrains. Obviously, it's a flat place. There is always static lighting, no changing lighting there, and there are no rain, fog, there's no weather artifacts at all. So it's a plain simulation. So a basic simulation looks like this. There's some walls and flat surfaces. So this works for an indoor environment because it's not very dynamic. But let's see if we have to get it for an outdoor robot. So for a Husky type environment, Husky is an outdoor robot. For that type of simulation, you need irregular terrains. You need to simulate change in lightings. You need to simulate weather. You need to have some common artifacts that you can manually place and create those simulations in real time. And we need to have, since we have weather artifacts and other things, we need to have some sort of models which actually affect the sensors and produce noise. So your algorithm that you are actually working on, that should adhere those problems, and that's the thing, bridging the reality to simulations. So my whole talk would be a basic pipeline. I guess there's some issue with the. Yeah. So my basic pipeline would be to create a blank simulation like this to something like this. So we have a car that is moving on a very rough terrain. This is a real life terrain that we have, and having some weather artifacts such as dust, it has houses, trees and everything. So we'll be going through a full pipeline, a whole story. So first let's talk to the real world terrain. So for the real world terrain we need two things. First is the elevation maps, commonly known as height maps, and the color data. So how do we get that data? First of all, we look it up in the sky. So there's a whole database for which was used to get the digital elevation maps using the SRTM mission. So that's how we can get the digital elevation maps. And for the color data, we have Landsat. Obviously, everyone knows that. So using the color data, we can generate actual texture maps, final texture maps using the QGIS format. And after combining these two, the textures and the height maps, we can create, we can add those in the SDF format for the simulation, and we can create something like this. Cool, right? So this is the real world terrain that we got for the Udaipur, basically it's a hilly area, actually from the Udaipur domain. So yeah, now we have the terrain. Let's head over to change in lighting. So the time of day. So for time of day, we particularly need a sun. So how do we create a sun? First of all, we need to choose which kind of lights to use. We need to see what type of which angle to be placed. The sun should be which angle, and where should be the sun present at. So first, which lightings to use? There are three types of lightings in Gazebo. There is spot lighting, there is point source, there is directional lighting. So in these type of lighting, which do you think is a more appropriate one to use? Anyone? Point source. Sun seems like a point source, but it is since sun is very far away, you can't actually use a point source. That is the right thing to actually think that sun is a point source, but we can't actually imagine that. So we need to use directional lighting since sun is really far away. So we need the light to be uniform in a given area, of course. So we need to choose an angle at which the sun should be. So depending upon the time of day, we can use a little bit of trigonometry. You can head back to the 11-12 basics and create a duration of time. And depending upon the time, we can actually create which angle the sun should be at. So let's say your day starts at 5 a.m. and sets at 7 p.m. So you can actually estimate where the sun should actually be. And depending upon the angle, you can actually check where the check the position where the sun should be. And once we have the angle and the pose, we can put it to code and we can create something like this. So here you can see sun is moving at different locations and the lighting is changing depending upon where the sun actually is. So you can just put in the time of day that you actually want and it will reflect it in the simulation. It happens automatically as well, but who is there to actually wait for 12 hours for a simulation? So now we have the time of day. Now we need to look at the weather artifacts. So how can we create weather conditions? So when we are outside, there is rain, there is fog, there is dust, there is snow, and list goes on and on. So to create those, we have particle emitters to the rescue. So yeah, anyone knows what particle emitter is? So it's something like a 2D array of images which has a lifetime and continuously appears and disappears depending on your configuration. So these emitters are highly configurable. So you can have particle texture, you can have particle shape, you can have particle size, you can have particle emitter size, particle velocity, and lots of things. So we can put our heads into it and see how we can actually create weather using these particle emitters. So we need to just brainstorm a little bit and let's see how we can create these. So if you have particles that are falling down with a smaller size, it appears like a rain. If you have particles that are emerging from the ground, it appears like a fog. If your particles are moving away from a certain location, it looks like dust. So you can create such artifacts that way. But it is not always like this is a type of weather you are going to get. You need to actually you need to be able to configure it somehow. So that's where we came in and we kind of developed a whole GIS which actually calculates, because not everyone is going to actually get those values correctly and manually feed in every time you run a simulation. So we need to actually configure it dynamically. So here's how, this is what we created. So for rain, you have rain rate, how much rain you actually want. You can position the rain where the particle emitter should be. For dust, you have done dust density. For fog, you have fog density. For dust, you can actually rotate where the dust from be emerging from and where should be its like final position. So that's how we can create weather conditions. Now let's see how to populate the world. Not in that way, but obviously the simulation is not just a plain world with elevation maps and sun or dust or anything. So we need something like models and everything to actually add it in the world and see like create a very realistic simulation. So that's how that's where Gazebo's resource spawner come in. And Gazebo's resource spawner is linked to a whole big repository called GZ Fuel. I guess every one of you might have visited it sometime or the other. So you can dynamically add it from the simulation, from the whole repository, and add it to your world. And you can create lots and lots of simulations just by putting these. So once we are done with this, now we head over to the most important part, like what's the point of all this? So the point was to actually create, actually add and reflect it in the sensor models, how it perceives in the sensor models. That was the whole point, how to optimize your algorithm depending on that. So yeah, that's where we can start with. So for sensor models, we have two things. First is the mathematical model, obviously, how the sensor is actually retrieving the data, and the noise model, how we can actually add noise to the sensor. So let's talk about noise here, because I guess I'm a little short on time right now. So let's see how particle emitter has effects on these sensors. So the particle emitter, if you can see in the depth camera, it shows a little of a blurry image in the depth camera, and your algorithm need to optimize that. In the in the RGB cam, you can directly see the whole particle emitter points. In the LiDAR, you can see the scattering of rays. The depth camera is obviously not affected by the particle emitter, since obviously you can't see. Like that's the whole point of depth camera. It should not be affected by that. And let's see some more effects that we need to add to actually see create a realistic simulation. So first thing is raindrops on the camera lens. So you can obviously see the rain in front of us, but sometimes when you're working outside, you can see these kind of effects. So the raindrops might get stuck on the camera lens, and your robot needs to perceive that. So for that, we can use a little bit of computer vision and create something like this. So we can get our image from the GZ and add a mask on top of it and add it to the real simulation to create a blurry effect. And to integrate it with GZ sim, we obviously cannot integrate it directly. So let's say we have a topic from GZ. We have a node that actually subscribes to that topic and adds rain effect on it. But to add the rain effect, since GZ and OpenCV are not based on the same format, we need to write a bridge. So the bridge actually takes in the image that we retrieve from the GZ and provides a CV matte image. And once we have that image, we can process it and send it back to another topic. So we can get a rainy topic and we can have something like this. So we have integrated this with the our rain model, and depending on how much rain is falling on it, it increases or decreases the effect. So you can see if the rain is medium, it has medium rain written and has medium rain drops falling on top of it. If it is high, then depending on how much rain rate you set in the GUI. So let's see another effect. So this is the lens flare effect. So anyone knows what lens flare is? So yeah, exactly. So when light flashes directly to the camera, it basically scatters. So you can perceive something like this. So this is due to the lens placement in the camera. So how can we create this in GZ? So with the help of Ogre 3D, we can have this sort of an effect. But to get that in simulation, we need Gazebo offers a very modular architecture that is called render pass. So render pass is a really useful thing for actually integrating these kind of effects, and we can directly take in the image from GZ and add these effects and set it back without any computational loss. So we add the lens flare class and add render pass to it so that SDF elements can directly use it. And once we code it up, we can create something like this. So in the opposite direction, there is light source coming from that, and if you can, it's not visible here, but if you can see, there is light actually dispersing at the bottom, at the corner of the box. And I'm really happy to see that the plugin that we wrote is actually integrated in GZSim now and is now available in GZ Harmonic, the latest version of Gazebo. And the whole plugin was built by Jasmeet Singh. So yeah. So now we are done with the sensor models, and once we are done with the whole pipeline, we can create some, we can add more effects. Let's see some more effects, such as there is car dust plugin, there is tunnel GPS plugin. So I'm just going to give a brief about that. So when you drive a car, obviously some dust might be falling behind, right? So if your robot is if you have self-driving cars, they obviously need to perceive that some dust is coming back from the other car, and you need to optimize your algorithm depending upon that. Same goes for tunnel plugin. So when we are working with ANS systems, so you need to see that when car goes inside a tunnel, the GPS confident value drops. So we need to integrate these things in GZSim as well. And this is just a gist of things that we have actually integrated in this. We have a lot more things that I am not able to cover due to the time foundation. So once we are done with all these things, we can create very realistic simulations like this. So you have fog, you have dust, you have terrains, you have models and everything. So yeah, that's the whole idea for the talk. Thank you. So, any questions? I would really encourage if any of you have any ideas how we can improve this anymore, because see, obviously we can't actually get all these effects without how user wants, which kind of, what kind of things users are facing in deployment of actual robots when they are transferring from simulation to real life. So if anybody has any ideas or any questions, just hook me up.
In simulations, basically we are building a URDF of the robot and spawning it in Gazebo and simulator.
Yes.
So when we are importing it into the Gazebo, we need some inertia tags for it.
Yes.
Even though the CAD softwares are able to generate inertia for the Gazebo, it doesn't always work well. So is there any solution or way to improve it?
I'm just giving a spoiler for the upcoming talk. So this is a talk given by Jasmeet Singh tomorrow. So he will be talking about a new plugin that is actually being integrated in GZSim, by which you can just give the density of the material that you have for the robot model, and it will automatically calculate the inertias for that.
So it will avoid drifting and jittering of the...
Yes.
Thank you.
So there are a lot more things in I have not covered in this talk, like robot models and some other artifacts that need to be added. So yeah, if any of you have any doubts, you can just meet me in person and we can have a detailed discussion after that.
Now people you know whom to reach out to if you have some suggestions related to all the kind of fancy stuff that Gazebo can offer you. Thank you so much, Naman. It was really insightful.
Thank you for listening.